Okay, ladies and gentlemen, welcome to the next part of the lecture. In this part, we shall be studying the derivation of inverse Dft. So, in order to derivate the inverse Dft, from the definition of Dft, we can write a part of the expression which goes like this. Now let us consider an arbitrary variable. Let L be any arbitrary variable which goes from 0 to n minus 1 and is identical to small n. So we can write summation where k goes to 0 from 0 to n minus 1. We can write this x of k as the direct transform. So the direct transform equation will be x of L. Since n is a variable, we considered a different arbitrary dummy variable L, and the limit goes from L, which goes from 0 to n minus 1. So omega n k L times this part omega n minus kn. This is simply the formula of direct transformation. Now, since the summation are independent of one another, and by the property of commutativity, we can interchange their position in the equation. And hence, we take this summation out, L which goes from 0 to n minus 1, x of L as it is independent of the variable k, we can bring it out of the summation, and the rest of the expression where k goes from 0 to n minus 1, omega n, and we just multiply these two terms. This becomes k L minus n. Let it be equal to r, say. Now, here we get two cases. Case 1 being if L is equal to n, then what will happen? Then omega n, here since L is equal to n, we can write k L minus L. This becomes 1 because L minus L becomes 0 and anything to the power 0 will become 1. And consequently, this whole summation where k goes from 0 to n minus 1, and since this value we have turned to be 1, so here it becomes 1. So summing 1 from 0 to n minus 1 will give us n. I hope that is clear. What we are doing is summing 1 for n number of times, so the value will be n. So this is the first case. In the second case, if L is not equal to n, then summation k goes from 0 to n minus 1 can be written as omega n k L minus n. This can be written as summation of k, which goes from 0 to n minus 1. And since omega n in our case is e to the power minus j twice pi over n k, we are replacing the value of omega n in this expression. So this becomes e to the power minus j twice pi n over n times k times L minus n. Taking this negative sign inside of the first bracket, we get k, which goes from 0 to n minus 1, e to the power j twice pi over n k n minus L. Now this is in the form of something like this, summation of a to the power x, where x goes from 0 to n minus 1. Let me rephrase it a little bit, it will become clearer. K, which goes from 0 to n minus 1, e to the power j twice pi over n twice pi to the power n minus L whole to the power of k. So this expression is something similar to this, and this from the geometric progression formula can be written as a to the power n minus 1 divided by a minus 1. So this expression essentially becomes summation where k goes from 0 to n minus 1 e to the power twice pi, there's a j twice pi over n k n minus L. This will be equal to e to the power j twice pi over n, and k is replaced by capital N. K is replaced by capital N over here as per the formula. N minus L minus 1 divided by e to the power, just the coefficient devoid of k, j twice pi over n minus L minus 1. Say this be equal to Aleph. This alphabet is called Aleph, and it is the first alphabet of the Hebrew letters. Say, so from the numerator we get e to the power j twice pi over n times n minus L minus 1. Here n cancels out, e to the power j twice pi n minus L minus 1. Now if you remember the derivation of the discrete-time Fourier series, where I have shown e to the power twice pi j theta will always be equal to 1 for any value of theta. So this expression will always be 1, and if this one becomes 1, this expression becomes 1, the result will become 0. And since the numerator is 0, since the numerator becomes 0, so essentially what Aleph becomes zero. So in the second case, when L is not equal to n, we get summation of omega n k L minus n will be equal to 0, where k goes from 0 to n minus 1. I hope this is clear. Now returning back to R in this case, which is summation of L which goes from 0 to n minus 1 xl summation k which goes from 0 to n minus 1 omega n to the power k L minus n will only have one value which is equal to n, and only for the condition when L is equal to n. Any other value of L, it will be 0. So since this value is only true for one condition, that is L is equal to n, so we can easily get rid of this summation because we need not sum over only one value. So this expression becomes summation L, this value we have found out to be equal to 1 as shown, n as shown over here. So we write this equal to n times, and what I have said that since L is only applicable for L equal to n, so this summation becomes void. We need not worry about this summation. We can simply write it to be x of L, and since L and n are analogous, we can write it to be x of n times n. So moving on to the previous expression, that is this expression over here, we can write this to be summation of k which goes from 0 to n minus 1 x of k omega wn to the power minus kn equal to x of n times n. So by the virtue of cross multiplication, we bring this to the left hand side, and this becomes x of n equals to 1 over n summation where k goes from 0 to n minus 1 x of k wn to the power minus kn, which is essentially our IDFT equation, inverse discrete Fourier transform equation. So I hope you understand this problem, this derivation. And moving on, in the next topic we shall learn DFT as linear transformation. Now then, DFT and IDFT, that is the discrete Fourier transform and the inverse discrete Fourier transform, can be viewed as linear transformation over a sequence of xn which is having a discrete Fourier transform pair x of k. So we shall try and justify this statement in this part of the lecture. So let us consider an endpoint DFT. What n point Dft essentially mean is that in this case n will go from 0 to n minus 1, and similarly k will also go from 0 to n minus 1. A point to be noted before I go any further is that in case of DFT, the number of samples in the time domain must always be equal to the number of samples in the frequency domain. They cannot be otherwise. So, in case of n point DFT, the length of the sequence or rather I should say the time period over which the sequence repeat is n. This will give us the direct transformation x of k summation where n goes from 0 to n minus 1 x of n wn to the power of kn, where obviously k goes from 0 to n minus 1. As I have said, it is an n point DFT. Now then, for the sake of simplicity, let us assume that suppose n is equal to 4. N is equal to 4. So, if n, capital N becomes 4, this expression will become x of k is equal to summation n which goes from 0 to n minus 1, not n minus 1, this is 4 minus 1, that is 3, x of n w for kn, where obviously k goes from 0 to n minus 1. So, breaking the summation operator, this can be written as the first sample when n is equal to 0, x of n becomes x of 0, and w4 to the power of kn, if n is 0, then w4 to the power 0 becomes 1. So, x0 times 1 is x of 0. Plus similarly, when n is equal to 1, x of n becomes x of 1. This term becomes w4 to the power k times 1, that is k. Similarly, the next term becomes x of 2, w4 to the power twice k, since n in the next term becomes 2. And finally, x of 3, where w4 becomes w4 to the power thrice k. Now, when k is equal to 0, in this expression, when k is equal to 0, x of k becomes x of 0. X of 0 remains as it is since it is independent of k. The next term becomes x of 1, w4, and k is replaced by 1, so anything to the power 1 is the same thing, so x of 1 times w4. The next term becomes x2, w4 to the power 2. I'm sorry, extremely sorry. Here we are working with k being equal to 0. Since k is equal to 0, this will become w4 to the power 0 will become 0, so we need not write it. w4 to the power 0 will become 1, and similarly x2 here, k, if k is replaced with 0, w4 to the power 2k will become also 1, and x3, w4 to the power thrice k, k being 0, will also become 1. So this is the first expression. and when k is equal to 1, x of k becomes x of 1, x of 0 remains as it is, x of 1. Now w4 to the power k, where k being 1 will give us w4, and consequently x of 2, which becomes w4 to the power 2, and x of 3, which becomes w4 to the power of 6, just replacing the value of k. I'm sorry, this is 3, because 3 times 1 is 3. It's a silly mistake on my part. So when k is equal to 2, x of 2 becomes x of 0 plus x of 1, k being 2, w4 becomes w4 to the power 2, x of 2, w4 to the power 2k, 2 times 2 is 4, so this becomes w4 to the power 4, and x3 becomes w4 to the power of 6. And finally, k, when it is equal to 3, x of 3 becomes x0, since it is independent of k, x1 times w4 to the power of 3, since k is 3, x2 w4 to the power of 2 times 3 is 6, plus x3 w4 to the power 3 times 3 is 9. So we get our 4 expression, and the above illustrated, this expression can be easily described within a matrix, and the matrix being matrix equation, where in the left hand side we have x of 0, x of 1, x of 2, x of 3, in the right hand side we are writing the coefficients of this respective terms. So here x of 0 has a coefficient of 1 multiplied to it, so this becomes 1. Similarly, the next term also becomes 1. This becomes 1 as well, and x of 3 has a coefficient of 1. In the next line, x of 0 has a coefficient of 1. X of 1 has a coefficient of w4, so this becomes w4. Consequently, the second one becomes w4 to the 2, and the third one becomes w4 to the 3. Similarly, for the rest of the lines, this will become w4 to the 2, w4 to the 4, and w4 to the 6, w4 to the 3, w4 raised to the 6, and w4 raised to the 9, which is multiplied with x of 0, x of 1, x of 2, and x of 3. So if you multiply these two expressions, we will get these individual lines. Let us verify one of them. In case of matrix multiplication, so what is the dimension? This is 1 times n, that is 1 times 4. The dimension here is 4 times 4, and here it is 1 times 4. So multiplying this one, x0 times 1 becomes x0, plus 1 times x1 becomes x1, 1 times x2 becomes x2, and 1 times x of 3 becomes x of 3, which is equal to the first element of the matrix in the vector in the left hand side. So this rather squiggly equations will be much easier when it is written in this matrix form. Now, as a matter of simplification, these vectors can be written as x being the matrix, the vector in the left hand side, the column vector, is equal to W4 times x. This is bolded out. This is the bold form. So this is the linear representation of the DFT. Now we have worked with how many samples? 4 samples. Now if we generalize the case for n number of samples, this matrix will look something like this: x of 0, x of 1, x of 2, which goes to x of n minus 1. This will be equal to 1, 1, 1, and this will be 1, 1. This one will be Wn to the power of 1, Wn to the power of 2, and consequently Wn to the power of n minus 1. Similarly, this will be Wn to the power of 2, Wn to the power of 4, Wn to the power of 2 into n minus 1. And similarly, this one will become Wn to the power of n minus 1, Wn to the power of 2n minus 1, and finally Wn to the power of n minus 1 times n minus 1. Which is multiplied with the time domain signal x of 0, x of 1, x of 2, which goes to x of n minus 1. So this is the generalized form of the DFT in matrix form. Let us mark it as equation A2. And this can be written as the linear transformation of x Wn times x, where x is bolded out, let us mark it as B1. I hope this is clear. So if we want to solve the DFT of a given signal, the matrix operation is much easier and less tiresome than operating with so many different equations. This becomes quite tedious. Hence we refer to the matrix form. And for your information, this matrix over here will have a dimension of n times n. This one will have 1 times n, 1 times n, and this matrix is known as the twiddle factor. Now referring back to this equation, if we multiply both sides by Wn to the power minus 1, this becomes x times Wn to the power of minus 1 equals to x. So this is the inverse transform. Why is it the inverse transform? Because here, if we multiply the twiddle factor with the time domain signal, we get the frequency domain signal, which is the direct transform. And the inverse twiddle factor, when multiplied with the frequency domain signal, gives the time domain signal, which is our inverse transform. And this will only hold true if Wn to the power minus 1 exists. So let us find out the value of Wn to the power minus 1, which is equal to 1 over n which goes over here to 1. And simply just change the power, that is negate the exponent of these w's. So the first one will become Wn to the power minus 1, Wn to the power minus 2, Wn to the power minus n minus 1, and so on. So this will become Wn to the power minus n minus 1, n minus 1. So rewriting this equation, we can write summation. This can be written as, if we take this to the left hand side, n times w of w to the power, there is Wn, to the power of minus 1 will be equal to Wn conjugate. And why is that so? Since we know Wn to be equal to e to the power minus j 2 pi over n, what is the complex conjugate of e to the power minus j to the power n? It is simply e to the power j 2 pi over n. So, which is in our case Wn inverse. This is nothing but a scalar factor. This doesn't affect the value of the matrices. So what I mean to say is that Wn to the power minus 1 is nothing but Wn conjugate. You can verify this with the Euler's relation. E to the power minus j can be written as cosine of twice pi n minus j sine of twice pi n over n, and this can be written as cosine of twice pi over n plus j sine of twice pi over n. So here the imaginary part is negative and here the imaginary part is positive. So these two are complex conjugates. I hope it is clear. And W of n times W of n conjugate will give us n times I of n, where I of n is nothing but an identity matrix with a dimension of n times n. So simply using the twiddle factor, we can easily derive the DFT and IDFT of any signal, and this is just a process to attack the mathematics or the problems that will be given in the exam or that we will try to solve. So that is the reason behind showing this matrix method. It will become much more clearer once we go into the problems, solving the problems. So I hope you understand, and let's move on to the next topic.